So we've looked at Gauss's law, and we had done some examples in other videos with some spherical symmetry, and you've got a different spherical one that you're going to be doing on the homework for me if you're in my class. Now we're going to take a look at some cylinders. And again, for students in my class, they will actually have to do some similar problems. But just going through here, and different textbooks have different things. So we had started with, when we were doing the cylinder example, looking at just a line of charge. That's the one that is typically used when you are doing general physics. So if you've got a line of charge, then we can construct our little Gaussian surface around that line of charge. And this is not a perfect diagram, but you got your Gaussian cylinder there, and so depending on how much charge you've gotten there, you're going to be able to go through and calculate that. So what I want to talk about now is not just a line of charge, but a cylinder of charge. So when we do that, there are a couple of different ways that we can approach this. And it's going to just cause our electric field calculation to be slightly more difficult than the line charge, but not too much. But just to remind you of our equation, I'm going to handwrite it just to make things easier again. You had the area of the Gaussian times the electric field was equal to the Q enclosed over epsilon naught. That's our basic Gauss's law. And we said that as long as you have cylindrical symmetry, such that the electric field is going out through the sides of the cylinder, and our cylinder is sufficiently long enough that I don't have to worry about the end effects, that I can find this because it's going to end up going to that the electric field is equal to the charge enclosed over epsilon naught, and then the area of the side of the Gaussian is going to be 2 pi r L, where r is the radius of the Gaussian and L is the length of the Gaussian. So it's important here to sort of keep straight a little bit what we're talking about, because our charge might be distributed radially with respect to the Gaussian at some cylindrical coordinate s. So for our class, we use the cylindrical coordinates of s, the distance from the axis, phi, the angle around the axis, and then z being the distance along the axis. So even though I've drawn it sideways, what we're really talking about in terms of our cylinder is this is the z-axis. So you could think of this as being an upright cylinder. It doesn't really matter. We can rotate coordinate systems as we've talked about before. So if you're outside of the cylinder, then we just have to find out the total amount of charge enclosed in the cylinder where the charge is. If you're inside the cylinder, we have to be a little more careful here. So I'm going to do just a general setup here for this Q enclosed part. Is going to be integrating of the dq, which is going to go to some sort of rho d tau if it's a solid cylinder. And again, in our cylindrical coordinates, the d tau becomes, you've got a ds, an sd phi, and then a dz. We're going to be able to use a Gaussian as long as this rho must be radial. In other words, rho can depend on S, but rho does not depend on phi or z. So again, we have to think about our limits of integration here. So if you are outside the cylinder, when we integrate from the center, where S is equal to 0, to the edge of the cylinder, misspelling that, which might be, say, at S equals capital R. And so this is a case where my distance R that I want to go so I'm just be careful here in how I am phrasing some things. So if the distance from the cylinder where I want to find the field is larger than the cylinder, and so then our integral is going to have my rho, which is a function of S, and just rearranging up here, S, ds, d phi, dz. And we would go from 0 to capital R, because after capital R there's no more charge, from 0 to 2 pi for the phi, and from 0 up to, say, some length of the cylinder. And it's important to realize here that my Gaussian cylinder has to be smaller than the length of the physical cylinder, such that we're near the center. And again, a lot of textbooks will talk about an infinite cylinder just to avoid this, but we've talked about how as long as you're not near the edge, that's all that really matters. Okay? So again, this equation for the Q enclosed is separable. And so we can write those out in terms, I've got 0 to L dz. I've got 0 to 2 pi of d phi. And then the interesting one, the 0 out to r of rho of s ds. And these ones are going to come down to some L and 2 pi, and then I still have to do this integral for some particular geometry. And so putting it together, my electric field at some distance r out from the center of the cylinder is going to be this charge enclosed, so I've got a 2 pi L on top, and then my integral. And that's over my epsilon naught and my 2 pi r L, which was the area of the Gaussian cylinder. And that's going to simplify down because my 2 pi L, I've got my integral up on top. And then on the bottom, I'm going to have an epsilon naught r. So I haven't specified my charge density. And when I specify my charge density, then I would be able to actually do the integral if it's a uniform density, for example, or if it's a radially varying density. And that's going to give you something up here on the top. And then I've got this epsilon naught over r. So I'm going to leave this video at this point and leave it as an exercise for you guys to look at either constant density and how that would work, or if you have a radial density, how that would work, and one of your homework problems. But all of the Gaussian symmetries where you've got some volume of charge, and it's a solid volume, is going to work out like this.